Welcome to doassignment-ca. Here is the problem. Gear A rotates with an angular velocity of omega A equals theta A plus 1 in radians per second, where theta A is the angular displacement of gear A in radians. Determine the angular acceleration of gear D when theta A equals 3 radians starting from rest. Gears A, B, C, and D have radii RA equals 15 millimeters, RB equals 50 millimeters, RC equals 25 millimeters, and RD equals 75 millimeters, respectively. Gears B and C are on the same shaft. Now let's work through the solution step by step. We are told that the angular velocity of gear A equals theta A plus 1 in radians per second. Substituting theta A equals 3 radians, we get omega A equals 4 radians per second. Here's the gear train layout. Gear A meshes with gear B. Gears B and C share the same shaft and rotate together. Gear C then meshes with gear D. The radii increase from A through D, giving us 2 stages of speed reduction. Here is the gear train layout. Gear A meshes with gear B. Gears B and C share the same shaft and rotate together. Gear C then meshes with gear D. The radii increase from A through D, giving us 2 stages of speed reduction. To find the angular acceleration of gear A, we use the chain rule. Alpha equals omega times d omega over d theta. The derivative of theta A plus 1 with respect to theta A is simply 1. So alpha A equals omega A times 1, which at theta A equals 3 radians gives alpha A equals 4 radians per second squared. Since gears A and B mesh, the tangential velocity at their contact point must be equal. This gives omega B equals RA over RB times omega A, which is 15 over 50, or 0.3 times omega A. Differentiating with respect to time, the same ratio holds for angular accelerations. Gears B and C share the same shaft, so they have identical angular velocity and angular acceleration. Therefore, omega C equals omega B, and alpha C equals alpha B. Applying the same contact velocity condition between gears C and D, omega D equals RC over RD times omega C, which is 25 over 75, or 1/3 of omega C. Differentiating gives alpha D equals 1/3 of alpha C. Combining both gear stages, alpha D equals 0.1 times alpha A. We can verify this by multiplying the two gear ratios. 15 over 50 times 25 over 75 equals 0.3 times 1/3, which equals 0.1. This is the overall ratio of angular acceleration from gear A to gear D. Substituting alpha A equals 4 radians per second squared into our overall ratio, we get alpha D equals 0.1 times 4, which equals 0.4 radians per second squared. This is the angular acceleration of gear D when theta A equals 3 radians. Here is a full summary. At theta A equals 3 radians, gear A has angular velocity 4 radians per second and angular acceleration 4 radians per second squared. Gears B and C on the shared shaft each have angular velocity 1.2 radians per second and angular acceleration 1.2 radians per second squared. Gear D has angular velocity 0.4 radians per second and angular acceleration 0.4 radians per second squared. We verify by checking tangential accelerations at each mesh. 15 times 4 equals 50 times 1.2, both giving 60 millimeters per second squared, and 25 times 1.2 equals 75 times 0.4, both giving 30 millimeters per second squared. The answer is confirmed. The angular acceleration of gear D is 0.4 radians per second squared. Visit doassignment.ca for more study tools, AI learning support, and online tutoring.